Hi everyone, today we're going to continue on with chapter 6. Today we're going to talk about factors that affect the SN2 reaction. So we're going to talk about the electrophile, the nucleophile, we're going to talk about solvent effects, and then we will have a brief summary of things that affect the SN2 reactions. So let's look at the electrophile first. So remember, electrophile or substrate can be used interchangeably. So an unhindered electrophile are going to be the most reactive than something that is sterically hindered. Which makes sense if you think about it, right? Because we have a backside attack of our nucleophile. So if we have a lot of steric hindrance associated with a molecule or an electrophile, it's going to be hard for that nucleophile to come in and attack. So if we have something that is a tertiary carbon, so something like this is going to be the least reactive. Basically, it won't be reactive by an SN2 reaction. Secondary, so secondary can be SN2 reaction, but it is not going to be as reactive as a primary, for example. And then the most reactive is going to be our methyl. Again, just because there's not a lot of steric hindrance associated really with that methyl group compared to a tertiary, for example. So let's look at some relative rates for a reaction. So let's look at this reaction here. And this should put into perspective the reactivity of a primary, for example, versus a secondary. So we have our RCl, so we have a methyl, primary, secondary, or tertiary. Oh, sorry about that. So our relative rates, you can see a very large difference between all of these values. And again, remember the larger rate is going to have a faster reaction. So you can see again, a tertiary is not going to proceed via a SN2 reaction. So let's look at the structure of the substrates or the electrophiles. So if we have something that is tertiary, for example, right? So this carbon here is going to be a tertiary carbon versus a methyl carbon. So your model kits would help you also to see this and think about it. So we have our nucleophile in both cases. So again, SN2 reaction, we know that we're going to have inversion of stereochemistry. We know that it's a one-step process, so the only possibility is a backside attack of that nucleophile. So what's going to happen is the nucleophile here can easily come in and attack that carbon, and this bond would be breaking at the same time. So here we have a lot of steric hindrance associated with this tertiary carbon. So it's going to be really hard for this nucleophile to get in and attack that central carbon atom. So again, it's just much harder for the nucleophile to attack that tertiary carbon. And that is the main reason that a SN2 reaction cannot proceed if the substrate is tertiary. Again, an SN2 reaction can proceed if it's something is secondary, primary, or methyl. We'll talk about some other factors considering if it can proceed via a SN2 reaction. So the next thing we are going to talk about is actually going to be the nature of the nucleophile. So an SN2 reaction will only proceed with a strong nucleophile. So now we have to think about what makes something a strong nucleophile. So any lone pair donor can act as a nucleophile. So this can be something as an anion or neutral species. So because the nucleophile attacks the substrate in the rate determining step, so remember rate determining step for the rate for a SN2 reaction is equal to K times the concentration of the nucleophile times the concentration of our substrate. So the nucleophile does play into the overall reaction rate of the reaction. So the stronger the species, is as a nucleophile, the faster the reaction. The more likely something is to donate a lone pair, the better nucleophile it's going to be. So strong bases are going to be strong nucleophiles. An anion is going to be a stronger nucleophile than its conjugate acid. Remember, Ca is going to be conjugate acid. So let's look at some examples. So in the last lecture, we looked at methoxy and quite a few examples. So that, again, is going to be considered a strong base, and it's going to be considered a strong nucleophile. So that's going to be stronger than its conjugate acid, which here would be methanol. If we look at this example here, this is also going to be a stronger nucleophile, stronger base than this compound here. We have our hydroxide versus water. Again, strong base, it's going to be a stronger nucleophile. When we're looking at this compound here versus this compound here, so this one would be a stronger nucleophile or stronger base versus this compound here. So another thing that we have to think about when we're looking at the nucleophile is we have to think about electronegativity. So remember the trend for electronegativity looks like this. So the more electronegative, En is electronegative, element has more tightly non-bonding electrons. So this is going to make it less reactive towards forming new bonds. So what this really tells us is the strength of the nucleophile is going to decrease from left to right following the increase in the electronegativity. So we're talking about in the same row right now. So let's look at some examples. So if we look at something like this, so again, this is going to be the better nucleophile versus something like this, an OH, again, because the oxygen is going to be the most electronegative, so it's going to be less reactive towards forming new bonds. If we look at this versus water, again, this is going to be a better nucleophile. This versus this, again, this will be a better nucleophile. Another thing that we have to think about when we're looking at the nucleophile is orbital size. So again, let's think of the trend for orbital size. So larger atoms are going to be more polarizable. So they are going to be able to have better overlap in the transition state. So if you think about this, if we have a more effective overlap, that's going to lead to a more stable transition state, which is then going to lower the activation energy. So if our activation energy is lowered, we're going to have a faster reaction rate. So looking at the trend, so now we're thinking about going down a column. So again, going down the column, the larger, the better overlap, which is going to make the transition state more stable. Lower activation energy is going to mean it's a faster reaction. So looking at selenium, sulfur, and oxygen, same exact trend. So going down the column, the selenium based is going to be the better nucleophile. If we have something containing phosphorus and nitrogen, so again, going down the column, same exact idea. So phosphorus will have it's going to be larger atom, right? So it's going to be more polarizable, and it's just going to stabilize that transition state and make our activation energy lower. The overall size of the nucleophile also is a factor that plays into the SN2 reaction. So the nucleophile strength decreases as the overall size of the nucleophile increases. But this makes sense if you think about it. So the more steric bulk that we have, that's just going to hinder the attack. So let's look at a series of possible nucleophiles. So looking at all of these compounds, this would be the best nucleophile just because it's less hindered. So as we add bulk to the compound or to the nucleophile, that is going to decrease the strength. If we think about resonance, so think about what resonance does. It's going to stabilize the lone pair. So if we're stabilizing the lone pair, this is going to make the nucleophile less reactive. So if we have resonance, again, that's going to decrease the strength of the nucleophile. So this would be a better nucleophile because this would have resonance. If we look at these two examples here, this versus this, again, this is going to have resonance. So this compound here does not have any resonance, so it's going to be a stronger nucleophile. Next, we're going to look into solvent effects. So we're going to talk about a few different terms that you guys may not be familiar with. Solvents are going to have a large effect on the rate of the SN2 reaction. So we're going to look at polar aprotic solvents. So what polar aprotic solvent means is it means that it can't hydrogen bond with itself. So polar aprotic are going to work best for an SN2 reaction. So they will dissolve the polar nucleophile, they will dissolve the leaving group, and they will dissolve the electrophile. Some examples of a polar aprotic solvent. So it's not important to memorize these solvents. If it was a solvent that I felt like you guys weren't familiar with, I would just show you the solvent on the quiz. But you do want to make sure that you understand if it would be polar aprotic or not. So we have acetone, which is a polar aprotic solvent. You guys have used this a ton in lab to clean all of your glassware. We have dimethyl sulfoxide, which is typically called DMSO. This is going to be a polar aprotic solvent. We have formaldehyde. Sorry, I don't know what just happened. So there you go. So we have dimethyl formaldehyde. So this is typically called DMF. Again, it can't hydrogen bond with itself. And then we have acetonitrile. So acetonitrile, this is typically shown as ACN. You'll see it abbreviated. So again, these are all going to be polar aprotic solvents. If we look at, so polar aprotic solvents are the only way that a SN2 reaction can proceed. So again, it's a lot to look at. We have to think about the electrophile, we have to think about the nucleophile, and we have to think about the solvent to know if an SN2 reaction can occur. We also have polar protic solvents. So if a polar aprotic solvent cannot hydrogen bond with itself, a polar protic solvent is going to contain either OH or NH bond for hydrogen bonding. So the most common that you guys will see are going to be water or alcohols. So what happens as the nucleophile, it's going to be solvated by our solvent via hydrogen bonding. So again, this nucleophile is solvated via hydrogen bonds. So it's going to make this sterically very large, which is going to reduce that nucleophile's strength. So if we want to react the nucleophile, what we must do is we have to desolvate or remove the solvent. And this is going to require a lot of energy, and it would increase the activation energy, which would then make the rate slower. So again, this is why polar protic solvents will not work for SN2 reactions. So another thing that will not work would be nonpolar solvents. So although nonpolar solvents would be ideal, they will not work because of the solubility issues. So we would have issues dissolving the polar nucleophile and the leaving group. So nonpolar solvents, an example would be hexanes. So again, nonpolar solvents will not work just because we won't be able to dissolve the nucleophile, the leaving group, maybe the electrophile, depending on what it is, in a nonpolar solvent. So lastly, we're going to talk about the leaving group. So let's think about the nature of the leaving group. So a group's ability to act as a leaving group is going to be directly related to its base strength. So weaker bases are going to be better leaving groups because they are going to be more stable anions. Good leaving groups are going to be electron withdrawing, since that CX bond must be fairly polar to make the carbon an electrophile. So electron withdrawing, remember, just means it's going to draw electrons away from the reaction center. So let's look at some good leaving groups. So some of these we have seen in the examples from the last lecture. So our halides are going to be good leaving groups. So something like chlorine, bromine, iodide. Another thing that is going to be a good leaving group that you guys will see will be sulfonates. So sulfonates will have this general formula here. So sulfonates are weak bases, which again is going to make them a good leaving group. So some bad leaving groups. So if we have a bad leaving group and we have a polar aprotic solvent, we have a primary electrophile, it would just mean that the reaction is not going to proceed. So some bad leaving group would be strong bases. However, their neutral conjugate acids would be good leaving groups. So something that would be good would be their conjugate acids. So something like water, an alcohol, or this R2NH. So another bad leaving group would be fluorine. So if you notice, we didn't include fluorine up here because we've talked about this quite a bit in class. So fluorine bond is going to be very strong. So it's just going to be harder to break. So fluorine would be a bad leaving group. So let's summarize the SN2 factors. So again, SN2 reactions are going to be one step. They are going to favor something that is primary or unhindered. Again, they can proceed via a secondary electrophile if it is a strong nucleophile, if we have a good leaving group, and if we have a polar aprotic solvent. So SN2 reactions need to have a strong nucleophile. A strong nucleophile, again, is going to be a strong base. And again, SN2 reactions will only proceed in a polar aprotic solvent. And again, a polar aprotic solvent cannot hydrogen bond within itself. However, it does have the ability to dissolve the nucleophile, the leaving group, the electrophile. So this would be our ideal solvent to use. So start practicing some of the textbook problems with SN2 reactions. So what our main goal for this chapter is going to be is you're going to see a series of reactions, and we want you to be able to choose, is it going to proceed via a SN2 reaction, which this is the summary for SN2 reactions, or is it going to proceed via a SN1 reaction? So the next lecture we'll be talking about SN1 reactions, and we will talk about factors that affect SN1 reactions. Have a great day, everyone.